So to simplify the notation, let's fix a prime p. So p is a prime number, positive. And maybe let's, so writing this is annoying. So let's write it as alpha, following the notation in the paper. I mean, this is this is an ideal p primary, so to speak. So first, in case 1, we can consider the case where p divides w, or equivalently p is smaller than small w by the definition of large W. In this case, this thing is written as slightly nice. Yeah, maybe before considering cases, let's note that if these ideas are all unit ideal, the unit ideal for then this event is trivially true always, because this latter group is the trivial group. So we are considering something that is always true. So this characteristic function is always 1, therefore the average is 1. Then this thing is 1. Yeah, let's assume this is not true. So for some I, this ideal alpha I is strictly smaller than the unit ideal. So under that assumption, in case 1, I claim that then our average is 0, because I mean, so I suppose yeah, because never 0 in this quotient group if this is not the unit ideal at this index I. This is easy. Let me see. So since alpha I is not the unit ideal, there is a prime ideal German p containing it. So take any such p, then we know that, so this contains the prime number p, because alpha yeah, because I was assuming so. Yeah, then so p, and I know that we know that and we know that p divides w, so it follows that this w part is in that prime ideal. But we know that bi is not in that prime ideal, but because by assumption this small b is co-prime to w. So if we know that this w is in this prime ideal, then the other one is not. So combined, it follows that this sum is not in the prime ideal p. In particular, it's non-zero. No, 0 in, I mean, or I can say that It's not in this idea, because it's not even in this idea. So this proves our claim in case 1. So the case 2 should be when P doesn't divide W. In other words, P is exceeding small w. So if we our claim is that if we further assume that P is sufficiently large, I mean some power L O N is the rank of our number field, the degree of our number field, and T, yeah, some power of L. The following is true. Sorry, in the statement of the theorem, maybe let me add the assumption that these linear maps have bounded coefficients. I mean, if yeah, because some arguments in the proof depends not on the specific size, but only on the size of the coefficients. So I want to make this aspect clear. So let me add the parameter L governing the sizes of the coefficients. The claim is that so if suppose that this alpha I is the unit ideal all for all but one index, so I0, then our average is the inverse of the norm of alpha I0. And secondly, if there are at least two indices such that this fails, so if alpha I is strictly smaller than unit ideal for at least two indices, say I and j, then we know that this we claim that this is at most the inverse of p squared. Yeah, this is not a complete computation, but for our purpose this turns out to be sufficient. So let's prove 1 and 2. So the map we are considering is the following. I0, and we only have to consider one summand because the other summands are 0. So the map we have to consider is this composite. So now P is prime to W. These are co-prime. So the map multiplication by W turns out to be an automorphism on the group in question. And also translation by a constant is a bijection on itself. So to compute the average, we can ignore the latter operation. So we are considering this kind of thing. So yeah, the quantity to compute is this thing. Therefore, our assertion follows from this map is surjective. I wrote, yeah, sorry. This exponent should have been yeah, this is an exponent depending on n, but the growth is faster than linear in n, so I should have written like this. So we want to prove the surjectivity, but recall that we are assuming that psi I0 is has finite co-kernel before going to the torsion situation. So it's true if P exceeds the order of the co-kernel, because then P will be prime to the order, and therefore if we go mod P power, the co-kernel vanishes. And we know that these linear maps have coefficients whose absolute values are bounded by L. That the co-kernels are, so by some linear algebra, these things have bounded size. Yeah, namely by the rank of the target, because it can be estimated by minors of the matrix representing the linear map. So we assume that P is large enough in the sense. Right. So this proves our assertion in this case. So let me go back and yeah. So we proceed to point 2. Assertion 2 is that so we assume that alpha I is not the unit ideal and alpha j is not the unit ideal. So we have to consider, I mean, at least we are considering, and we project down to the sum of two components, because we know that at least these two components are non-trivial. So our assertion was that the probability where of the event that the given element here becomes 0 in here is at the most 1 over p squared. So that probability, that the event that something becomes 0 here is lower than, is rarer than the event that it becomes 0 here, because there is an implication that if something is 0 here, then it is 0 here. So our assertion was like this. So our assertion follows from the assertion that this composite has image of order at most p squared, and we can prove it because so we know that the kernel of psi I is not contained in kernel of psi j, So we can take something here, xi maybe, which doesn't belong here. So since we know the other direction, we can take an element xj here, which doesn't contain, which is not in the left hand side. And so let's consider these guys, a class of xi and class of xj. And the first element, let me see. So this goes to, so since it is in the kernel of psi I, the I component is 0, and I claim that the j component, the j component is non-zero under the assumption that p is large enough. So why non-zero? So I mean, so a priori we only know that this thing is non-zero in OK, but it turns out that since this guy is non-zero in OK, I mean it follows that so only finitely many prime ideals contain this guy. So I assume my prime number p is large enough to exceed all of them, exceed the norms of them. So it follows that under that condition, it is also true that this element is not contained in alpha j, because alpha j is a p typical ideal. Yeah, so symmetrically I know that this becomes like this. Therefore they are linear combinations of the at least p squared elements, right? Because because each of this and this are p primary torsion abelian group, and I have a non-zero element in such a group. So there are at least p multiples of such an element in this group, and also here is and it's also the number of their combinations is at least p squared. This proves our assertion 2. So this has been proven. Yeah, to summarize, let me go back to our old notation. So we have computed this has been computed as 1 if and it becomes 0 if p divides w, and certain value I0. if P exceeds small w and the small w is assumed to be larger than a certain power of L. I mean, of course, this latter part, so this, the threshold for this to happen can be also given by some linear algebra and something, and this gives us threshold of this type for P. I mean, because we can find these elements algorithmically, depending on and the size of the entries of these vectors can be bounded by the size of the coefficients of your linear map, because it's a linear algebra algorithm. Yeah, so this is the summary of our computation, and let's note that in the third case here, so this this will be 1 over P when this ideal has norm P. So it means that the residue ring is the finite field with P elements. So it is a prime ideal of degree 1. And it's equivalent to one of the following. So this, I mean, over P. So either this and this are both this, or this thing is German P, and the latter thing is the unit ideal, or vice versa. So these three cases. And else, so this will be bounded by the reciprocal of P squared anyway, so then we will have the same conclusion in any case. So what is truly special is this case, and else it's not so different, not so interesting.